So these are, let's see if we can zoom out here. So these are our three laws of motion, and Newton borrowed heavily from Galileo. Okay, Galileo really basically came up with the first law there, and the first law is a breakthrough. The first law is a breakthrough. The first law can be summarized this way: that objects resist a change in their motion. Okay, and this resistance to a change in their motion is called inertia. Okay, so objects have inertia. And inertia is a resistance to any change in motion. So objects will tend to keep doing what they're doing. And this is a breakthrough because before Galileo, there was Aristotle, and Aristotle just said, well, objects tend to sit still. Look, every time I try to move an object, it'll sit still. Right? I move it that way, it stops. Right? If I go into a racquetball court and I just smash a racquetball, it bounces around crazily, and if you avoid the racquetball, eventually it's going to bounce itself and stop moving. Yeah? It'll take a while, won't it? But eventually it'll stop moving. So this is what Aristotle said. And of course, we have a more sophisticated understanding of this. It's not that objects tend to just sit still. What is it? Why did the object sit still? Yeah, there's a frictional force that's actually acting on the object. And the friction force is what's making it sit still. If we could somehow reduce the friction, this is what Galileo surmised, right? If we could get rid of friction, then objects like the Earth could move around the sun for 4.5 billion years without like jet engines pushing on it to make it go around the sun, right? You have to, in order to understand how the universe really is, you've got to have inertia, don't you? Okay? The Earth is rotating about its axis once every 23 hours, 56 minutes, and 4 seconds. Okay? It completes one rotation, and it keeps doing that, and it's been doing that more or less at the same rate for 4.5 billion years, right? And that's because that's the tendency of objects, is to just keep going. We're all moving that way at about 1,100 miles per hour, or something thereabouts, around 1,000 miles per hour, right? We're moving that way, and it's like, gee, it doesn't seem like we are. Well, that's because everything has inertia. It keeps going that way. When I throw this up in the air, it's not landing in the same place, is it? Definitely not. I mean, it's like I threw it here, and then it's not, well, you know what I mean? Right? And besides that, it's 19 miles a second, so it's reckoned around the sun, right? So you have to have inertia. You have to have this concept that if you could get rid of friction, that objects would just keep going in a straight line at a constant speed, right? And every part of the motion would stay the same. If I threw a baseball into outer space, and I was in outer space, far away from any mass object, right? Everything about its motion would stay constant. It would move at a constant speed in a laser straight line. The rotation of the baseball would be the same exact rate. The axis of orientation of the rotation would point in the same direction, right? So yeah, I mean, this is a revolutionary idea, right? So here, this is the best I can do. I don't have a frictionless surface, but I do have an air track, which is going to float this glider on air so that it'll be close to frictionless. And here I've got a very powerful blower. This is how I do my hair in the mornings. I'm drooling. So if I hook this up to the air track like this, it essentially has no friction. That's very nice. A little applause. And it won't go forever. It's not truly frictionless, right? It's but it's as close as we get. When we do the conservation momentum lab, we're going to do like a collision on these things, and we'll analyze it. And if you look at it closely enough, sure enough, there is enough friction that if we use photo gates and super accurate microsecond timers, we can actually get that momentum's not conserved, even though it probably should be, right? So that's the notion, right, is that this is the tendency of objects, is to just continue in a straight line at a constant speed, right? Unless there's an outside force acting on it, right? So then the question is, what's an outside force? And if there's an outside force, what's an inside force? Then we know the answer. I can give you an example of an inside force. When we were little, okay, we drove a car, and the car would slow down on hills. Now this is a concept foreign to you guys, Okay? You probably have a car that can just go up hills and not slow down. But back in the 70s, they were concerned about fuel consumption. And so my sister had a Volkswagen diesel Rabbit that got 60 miles per gallon. 60 miles per gallon without hybrid technology. How did it do this? It had a tiny diesel engine. Now, you could go 75 miles an hour on it, but if you went up any hill, you were going like 45 and belching smoke, right? Yeah. Okay. So the cars slowed down. Nowadays, Honda Accord, just an ordinary run-of-the-mill car, right? Okay, has 190 horsepower. This is amazing. That Volkswagen van that you saw in the slideshow, okay, that thing had a 30 horsepower engine, 30. Yeah, it could go highway speed, not uphill, not with a headwind, not with the rag top pulled back, right? Okay, but if you sleeked it all down, closed all the windows, had a level road, it would go 55, 60 miles an hour. Right? So this is my little tirade here, right? We now want power. We want to be able to pass. We want to go, right? And we don't care, I guess, as much about fuel efficiency or something, right? Okay, so where are we going with this? Inside force. The car would be slowing down, going up a hill. My parents would say, and this was their joke, and they always made this joke, push on the seat. What that meant was we were sitting in the back seat, yes, and we were supposed to push on the front seats. Does that work? Is that going to work? No, that's not going to help the car go up the hill because that's an inside force. So an outside force is a force from outside of the object. So in this case, when I give that thing a shove, this is the outside force. So it tends to sit still. Whoops. Object at rest will remain at rest, right? I'm just leveling this. But here's an outside force. Ta-da. Okay. So that's our first law, right? Is basically objects have inertia, right? And then if the second law says that if there is an outside force, right, that the force and the mass and the acceleration are related this way, right? Or another way of saying this is that if there is an outside force, okay, then there is an acceleration, and the acceleration is directly proportional to the force. Yeah? So the bigger the force, the bigger the acceleration. It's inversely proportional to the mass, so that the bigger the mass, I'm liking that not so much, but the bigger the mass, the less the acceleration, right? So the concept here is that that mass is a measure of that inertia. The bigger the mass, the less acceleration you get, yeah? Okay, does that make sense? Right, so this is why, in shot put, right, the big shot put's harder to put, yeah? The small one is easier to put, right, if that's the verb, right? And anyway, there we have it, and we'll talk more about this, but this is the notion, right? And then the third law, you could summarize this way: for every action, there's an equal and opposite reaction. If we were to have you floating in space, da-da-da, if you can imagine that, right, and here's your friend floating in space, ta-da. Okay, there you are, just floating, free floating, right? Maybe in the space station. There is no way, unless one of you is tethered to something or attached to something or has some form of propulsion or something like that, but even then it would still apply, right? There's no way for you to push them this way without you being pushed this way. There is no way for you to send them flying without you flying backwards. Now, if you have different masses, you're going to move at different velocities. If you're heavier than me, I'm going to go faster and you're going to go slower. Yeah? But that's the notion, right? That's our third law. Or if I have a rifle, right, and I shoot the rifle, if I shoot the bullet that way, the rifle goes this way. Yeah? Or if I have a rocket engine and I shoot explosive gases, products of combustion that way at like Mach 2, I get pushed this way. Okay? So that's our third law. And the question some kids have is, well, why is it that way? And we don't know. It's just one of the rules. It's a game of chess, right? We're watching this chess game. We don't know why the rules are that way. They just are that way, Okay, so at this point we've got this. We also have some stupid teacher tricks that we need to do, and most of these things demonstrate inertia. But I do have a really good Newton's third law demonstration. Okay, but our first demonstration is this is pretty basic. We've got a tin can.